And hello everyone, welcome to our video on turbulence modeling. So in the last video we talked about some of the smaller scales within natural convection. These are the bachelor scales. I don't know if I pronounced it right, but yeah, basically we talked about how to roughly derive, just some of the steps. I skipped a lot of steps because I didn't want to bore you with too much information, and frankly, unless you're very into all these nitty-gritty theoretical stuff, I think it's just good to just summarize all of these and just present the final results that the Kolmogorov scales here, they're dependent on the Prandtl number, the Nusselt number, and the Rayleigh number. For what reason, I already kind of explained that your dissipation rate is the same as your energy input rate, and that is dependent on the Nusselt number, which is the amount of energy you put into this whole turbulent system. And if you have a bachelor scale, it means that your thermal conduction becomes kind of important. Therefore, you need to think about how to diffuse the energy away via conduction, and that will probably pertain to the bachelor scale, where this conduction is more significant than, say, the viscous dissipation. So these scales, like this in large Prandtl number fluids, this bachelor scale is usually smaller. Alright, so that's what we went through. And let me give you a rough idea of scaling. For flat plate flow, Nusselt number actually scales to the cube root of the Rayleigh number. And also the same is true for Rayleigh-Bénard convection, where you have the hot plate at the bottom and the cool plate on top. Just to remind you what Rayleigh-Bénard convection is, it is like this. And the flat plate convection here, this is a single flat plate flow, where natural convection current is just flowing upwards. Now, of course, we want to move on to something a little more complex, such as mixed convection. So now the thing is that we have three scales in play. We have the Kolmogorov scale based on the Reynolds number. Alright, based on the Reynolds number. Or in the natural convection case, okay, so this is the forced part of this mixed convection, because in mixed convection we have forced convection and then we have natural convection as well. So there are like three scales. So for the forced convection, we just use the Kolmogorov scale, which is based on the mean Reynolds number. And if you think about natural convection, you have two more scales over here, which are this Bachelor and Kolmogorov scale. One of the ways is to just pick the smallest of the three. Okay, pick the smallest of the three, and it'll give you a rough ballpark figure into where you can start sizing or scaling your smallest mesh size. Of course, in most literature, if you see this natural convection and forced convection together in literature, sometimes, most of the time, you might see that the forced convection is much more significant than the natural convection. So you have a low Richardson number. If you remember what Richardson number is, okay, Richardson number equals to Graw divided by the Reynolds number squared. So for low Richardson number, you can see that the forced convection bit is a lot stronger than the natural convection bit, which is described by this Graw number. Okay, so so in literature, what you might see is that the wall spacing is based on the wall shear stress. Okay, wall shear stress. Okay, for a tube that is in like r theta z, or in this particular example, you have r, you have phi, and then you have x. So in the r direction, your mesh will change from 0.17 all the way up to 5.1, because as you can see here, it looks like, from this you can kind of infer that perhaps forced convection is a lot stronger than the natural convection. Therefore, your grid sizing is dominated by the forced convection bit. That makes it kind of simple, because then you can use all your usual pipe flow or your usual pipe flow correlations, or your flat plate correlations, whatever correlations you have. You can use that to estimate the friction Reynolds number, and that will help you figure out how to get the true mesh size in terms of these wall coordinates. So just not to confuse you, these are basically r, theta and z, except you write it in a slightly different form. So these are basically r, theta, z, but this gives you an idea of this grid spacing. Now the thing is, with these scales, this Kolmogorov scales and the bachelor scales, okay, in bachelor scales, we don't really know how they compare in scale to this wall shear stress units, wall shear stress based units, because these are based on the friction velocity. So for now, I'd like to give you one example to see how these wall coordinates based on the wall shear stress actually compare to, let's say, the Kolmogorov scale. So this is we can start by estimating friction velocity for the force flow. Of course, you can talk about natural flows later on, but we talk about the simpler case first. Okay, so remember that a wall shear stress is needed to predict this friction velocity, and that will actually give you the non-dimensionalization you need to get maybe r plus or y plus or x plus. So if you remember, let's say y plus, that is actually equals to y, but you kind of scale it with the friction velocity and you divide it by the viscosity. That gives you the dimensionless, what do you call that? Units at the wall. So these are for your standard correlations. Alright, so how do we figure out this friction velocity? Because viscosity is quite easy for us to find out. It is just this friction velocity that we need to do. So for example, let's say we go for pipe flow, very simple flow. We have this thing called the friction factor, fanning friction factor. Okay, from Moody's chart. I mean, there may be some other charts that will give you some other kind of friction factor, but you should know most of these friction factors, only the coefficient in front kind of changes from Darcy or whatever. So the coefficient in front kind of changes, but mostly the scaling here is preserved. It is tau over rho u mean squared. So this, you just watch out for whatever coefficient you have in front, and that'll be fine. And this will help you get your tau wall, which is what you want here. All right. So this will give you an estimate for the wall shear stress. Okay. So it's not like you just do it once and then it's fine. You still need to check your CFD or whatever for your real wall shear stress. Okay, the real wall shear stress you actually have, in order to see whether your units are enough. The grid is fine enough. Okay, so you look out for your mean wall shear stress, and that should give you the right units, or maybe your maximum wall shear stress if you're that picky. Okay, so how do you calculate this friction factor without always looking at the graph? Okay, so from Churchill, in Perry's chemical engineering handbook, this is one of his correlations that will help you to calculate this friction factor. What is this? What is this friction factor? It is based on this correlation here, and that is based on the mean Reynolds number. The mean Reynolds number here. And this one is of course the roughness ratio. I mean, this epsilon here is the surface roughness, and this is like some pipe diameter. Okay, but for DNS, we mostly ignore the surface roughness, because if you really want to include surface roughness, maybe you have to make your edge a bit jagged. Okay, because for DNS we want to simulate virtually everything. I mean, if that is the spirit of how you do things, then you probably want to have actual jaggedness at the edge to simulate all this surface roughness, if you're that into it. Okay, otherwise you have to use some sort of model, which is not what DNS is about. So for most of the time in DNS, we like to use smooth surface as a comparison. So for simple case, we will just assume this roughness ratio is 0. There's no surface roughness. It's completely smooth wall, or at least this bit here is negligible, at least compared to this factor over here. Okay, hopefully that's clear. Just want to clarify whether this logarithm here, is it logged to the base 10 or ln of x, because if you check Perry's handbook, they just put a 1 log over there. Now, rule of thumb is this: if you take a paper from the 1960s, 1950s, the older you get, the more likely people are to use this log to the base 10. All right, people like to use log to the base 10 in the 1950s and 60s for some reason, and nowadays people like to use the natural logarithm ln. Okay, so for quick calculation, I did just to check that was really log 10. Okay, you have a Reynolds number mean of about 5,000. Okay, and if you check the Moody chart, the friction factor here is about 0.0091. And if you calculate this in a value, you substitute 5,000 in here and you substitute 0 into here, then you will just get this correlation here where 1 over square root f equals to 10.2739. And you just swap around and calculate your friction factor and you get 0.094738. Okay, so it's about 0.094, which is pretty close to 0.0091, which means you are roughly in the correct order of magnitude, which means that, yeah, it's a good match. So how do we correlate? How do we get, I mean, this is a lot of formulas, isn't it? You have this friction factor f, which you kind of have to manually calculate, and then you want to correlate this to tau wall, and tau wall you kind of want to bring it here, all that kind of stuff. It's kind of a bit annoying sometimes. So how do we just have, let's say, the Reynolds number, the mean Reynolds number correlate directly to U tau for smooth pipes? So this is a smooth pipe correlation. So can we do it? Absolutely. And so I'm just going to show you some of the steps in derivation, or maybe all of them. Okay, so I just substitute this f over here. All right. So tau wall equals to f times this half rho u square mean. So that's what I just substitute here from this equation. Substituted in this into here. I divide out the densities out, cancel that out, and this is what I'm left with. And this actually makes a very nice correlation over here, where you can just bring the u mean square out here, and then you just have a nice half square root f. Now the nice thing about this is that square root f is kind of over here. It's already based on square root f, so you can kind of just swap it around so that you have square root f equals to 1 divided by this minus 4 log 10 whatever. Okay, so we have a correlation for u tau in terms of u mean, and of course this correlation. Unfortunately, of course, this correlation is still kind of messy. All right, so we want to tidy things up. Okay, so sometimes we don't see u tau in literature. We usually see the Reynolds number, the friction Reynolds number. Remember, it's usually about 180 for DNS simulation. Lots of literature has DNS simulation about 180, and there's a reason for that. I can show you a little shortly. But how can we have it correlated to, let's say, RE mean over here? You already have RE mean over here, which is non-dimensional, which is nice and tidy. We kind of want to tidy these two terms up as well. So, okay, so sure, we multiply both sides by this L over nu, where L is the length scale of the pipe. Nu is this what do you call that? Kinematic viscosity. So the length scale of the pipe is of course the diameter. So this L is equals to D. Okay. Okay. So if L equals to D, pipe diameter, then you can just say this. We just have UD over nu. Then if you define your friction Reynolds number as such, then we define RE tau equals to U tau D divided by nu. Then that's fine. You can say that this side is the friction Reynolds number, and that's equals to RE mean times all this nonsense over here. not exactly nonsense, it's correlation. So you can see that you have this Reynolds number mean, and if you know the mean Reynolds number, you can calculate the friction Reynolds number, and by doing so you implicitly calculate this u tau, and that actually helps you a lot in finding your friction velocity and of course your wall scales. So what is this then? Can we actually not, can we simplify this even further, because we don't like all this logarithm stuff here. So if you want to do that, it's still possible. If you don't want to remember everything, we can just simplify for smooth pipes like so. So what I did is I assume this to be 0. I set this to 0 for a smooth pipe, so I get this correlation here. And what I do, I plotted this in Excel. Now one more, again, I want to remind you, I want to remind you to be careful what length scale you're talking about when you use this formula, because this only applies to pipes and all. So you have to be careful what length scale you're talking about when you take this friction Reynolds number here. Alright, so don't make the careless mistakes. Okay, so thankfully for us, this thing actually turns out to be a very linear correlation. So the Reynolds number, the mean Reynolds number and the friction Reynolds number are linearly correlated over a wide range of mean Reynolds number. So here I actually plotted in Excel and just show you the results quickly. Okay, so what I did is I have one cell saying, okay, you have the mean Reynolds number to be like so, and the other cell says okay, I have the friction Reynolds number to be so and so. Okay, cool. So what does this correlation actually help find? What does it give us? So it shows that we have a linear correlation, that we have Ra tau equals to about 5.72 times 10 to the minus 2 Re mean plus some intercept here. So note that most of your Re tau here is actually on the order of 180. You see the at 180 over here, at 180, Re tau about 180. That's actually just nice, the Reynolds number of 2300. This is actually critical because that's where your turbulent regime actually starts. So that's important for us to know. We have onset of some turbulence in this regime, and of course over 4000 we know that our regime is for sure in the turbulent region. So that's why we say this 180 is a pretty important number. So that's where we have statistically large amounts of turbulence happening in the smooth pipe. So that's based on how I define Re tau and Re mean. Okay, so we have a linear graph. So you can just look at this correlation here, 5.72676 times 10 to the minus 2 times Re mean plus 5.51. Okay, so yeah, I gave you as many decimal places as I could so that you can use this properly. It's about 5 decimal places, should land you roughly in a good ballpark figure. So now on to the example. Now that you have this correlation, how can we get our x plus, right? We want our dimensionless coordinate system. So I have x plus equals to x times u tau over nu, and it looks just nice. This u tau over nu is very much in common with our friction Reynolds number. So that makes life a lot easier for us, rather than having to think about what is the kinematic viscosity, what is the u tau. So you can skip all those steps if you know the friction Reynolds number here. So as long as you know your length scale, which in this case your friction Reynolds number's length scale is based on the pipe diameter, so you can write it in this manner. This u tau over nu, you just divide this equation throughout by L, and then you get Re tau over L equals to u tau over nu. And then you can write it in this manner by substituting this into this equation here, and you get x plus equals to x Re tau over L. So now you have something you can really work on. You can just have a friction Reynolds number and the pipe diameter, and immediately you can find out what your wall scales are. So now for the interesting bit, let's do some comparison. let's say we have a flow of Re tau equals to 180 as we defined it. The mean Reynolds number is 2300. So this is okay, decently turbulent. So if you have a DNS, you want to do a DNS, alright, what should your mesh size be for, let's say, a 0.1 diameter pipe? So we know that our smallest DNS mesh is about 0.05 in dimensionless wall units. So delta x equals to 0.05. Then we just substitute this into the equation here. So x equals to 1 over Re tau over L plus times x star, x plus. Okay, so x plus is the dimensionless unit, which in this case is 0.05, and this is the smallest DNS mesh you will ever get. So this is sort of a lower bound. Alright, then we just substitute Re tau equals 180, L equals to 0.1, and we substitute in here, and 0.05. Okay, sure, cool. And this will be 2.77 times 10 to the minus 5 meters. We are talking about micrometers here, micrometer scale. Or you can talk about in mm scale, 0.02777 mm. So this is a very, very small region. Just for curiosity's sake, how thick is this viscous sublayer region? So x plus equals to 5. We do the same substitution and we see, oh, the viscous sublayer is in the range of about 2.7 mm. That's pretty thin. If you think about 0.1 meter pipe is a 10 cm pipe, okay, viscous sublayer is about 3 millimeters thick, biggest. And what is the boundary layer thickness estimate? We know that the boundary layer thickness, we have a x plus or y plus of about 500. 500, okay, let's substitute this in. So 1 over 180 plus times 0.1 times 500. So we substitute everything in and we find that, oh, okay, we find this, okay, we have 1 over 180 times 0.1. So we get this number. Then we find that the boundary layer thickness is 27.8 centimeters. Now if you think about it, I mean, I'm just crunching numbers here, but 0.1 meters is actually 10 centimeters, and this is actually at 27.8 centimeters. So you find that your boundary layer is actually, you know, your whole pipe flow. Your whole pipe flow is like, because it becomes a bounded flow, which kind of makes sense. It kind of makes sense because, okay, fair enough, cause you know that your log law regime kind of works. Okay, maybe it works, yeah, but this is a very, very low turbulent flow. So there's almost like no the free shear region is like small or almost non-existent. So yeah, but if you increase, of course, your friction Reynolds number, you increase your friction Reynolds number by, let's say, 2 to 3 times. Maybe you get a friction Reynolds number of about 500. Then you will see to say, okay, this boundary layer thickness may actually be smaller than the so-called pipe diameter, so to speak, or 2 times the boundary layer thickness is smaller than this pipe diameter at a higher friction Reynolds number. So this one is kind of okay, sure. I see that the whole flow inside is pretty bounded. Okay, but this gives you an idea of the scale, the magnitude of this. So pretty much your whole simulation here is within the so-called x plus or y plus equals to 500. So cool. Okay, that's something to take note of. Okay, so this for low Reynolds number flow. And how does this compare to the Kolmogorov scale? It's very interesting. So eta over d, where d is the pipe diameter. Now eta is this Kolmogorov scale. So it's equals to 1 over, approximately equals to 1 over 3/4 Reynolds number mean to the power 3/4, or 0.75. So this is the ratio. So this is the ratio here, and we find that, you know, see the Kolmogorov scale. The Kolmogorov scale here is 0.3 mm. Okay, 0.3 mm. If you take a look at this, it is actually about 10 times smaller. 10 times smaller than this viscous sublayer region. Okay, it's about 10 times smaller than the viscous sublayer region. That's very interesting for us to know. But if you think about it, If you think about it, it's about 10 times bigger than this smallest mesh size, which is 0.03 mm or 0.02 mm. So this is about 10 times bigger, 10 to 20 times bigger, somewhere in that range, or 15 times bigger actually. So it's interesting to see that, okay, your Kolmogorov scale here is actually on the order of the smallest mesh size you actually use, or about 1 order of magnitude bigger. So that's just a good rule of thumb for you to know. So if you want to take a look and be very stringent, the Kolmogorov scale is equals to delta x plus times L over RE tau. If you just substitute this in here to here, you'll find that the delta x plus is equals to 1.85. So the Kolmogorov scale here is about on the order of these Moore units, dimensionless Moore units. Of course, this is for this case only, or in general with a low Reynolds number, DNS with a smooth pipe. But we can see the rough relationship here. They're very, very about the same order of magnitude. So that's a very interesting thing for us to know, at least for this low Reynolds number flow. And yeah, I'll stop now. Thanks for watching. I'll see you guys again. Bye bye.